Again, you can download this material from this website. So if you want to look deeper to data or later on, you can get the material from the address shown below. So I'm VP again. So VP easier than Veli-Pekka. So go ahead and use VP. Okay, I will talk about third order intermodulation distortion. So this is a not very well known topic, and it can cause a major trouble for all the Wi-Fi. So let me start with a simple block diagram of Wi-Fi receiver or any receiver, but just a Wi-Fi receiver here. So what we have there, we have antenna, then we have a low noise amplifier, and then some mixers to down convert and detect the signals. So in Wi-Fi, we do not have here typically any filtering, or if there is filtering, it's not very steep. So it means that different signals, different frequency bands enter the receiver pretty well. So like you can have GSM or 3G LTE signals entering the receiver as the Wi-Fi signals with the same levels roughly. There is some antenna behavior difference and so on, but basically enter the same signal levels without filtering. Okay, so two signals enter the receiver, high-level signals. So what we are missing there typically is a filter which blocks out everything else outside the band. So it lets through only the Wi-Fi signals and blocks out those cellular signals or other signals which may get into the receiver. So this is very important. It's usually not there, or it's very has very limited filtering characteristics like this. It a little bit kind of filters out the edge of the peaks. Okay, so how this intermodulation happens is that you have those two tones at different frequencies entering the receiver. So when the signal level increases, the linearity or non-linearity of the receiver will start growing here two different products, intermodulation products, next to these carriers. And these grow very fast compared to the signal level. When you basically increase signal level of these by 10 dB, these go up by 30 dB. So they are third order intermodulation products. So the frequency they are on is, you have here a difference between these two carriers. So these third order products are at the same distance from the carriers as what is the frequency difference between these two high peaks. So this is different than the harmonic products, which are multiples of the original frequency. Okay. So this describes the linearity of the receiver. So this is output power, input power. When you increase the input power, the output power increases linearly. When you get into the nonlinear range, the output power starts to kind of saturates and eventually saturates. No matter how much you put more input power, output power doesn't go any more up. You are saturated there. Now, this nonlinear operation happens when you start approaching this point here, this corner here. So typically there is about 10 dB peak to average ratio in Wi-Fi signals and LTE and other signals. So you need to stay at least 10 dB out from this, these levels where the receiver starts to get into the compression to stay out of this trouble. Okay, so different scenarios how you can see these problems. So these are different frequency bands. These are European frequency bands, but same applies to US, just different frequency bands, which is important, of course, what is the band and where. So in one scenario, you can have an LTE band here next to the Wi-Fi band, carriers are basically near to each others, and then the difference lands to the Wi-Fi spectrum. So this is one case. By the way, if you enter two very high signal Wi-Fi signals within the band to the receiver with high duty cycles, very high power levels, you will see the same impact there as well. So this is one case. Second case is that there is something above the Wi-Fi band. So again, the difference of these, you come down again to the Wi-Fi band here. So there is your IMD carrier. So then third case. So and this, I have more information on this case, some measurement data. So we have a carrier here, another carrier here, and when you take the difference of these, you end up to the Wi-Fi band again. And these are not filtered out in the receiver, and filtering them at the transmitter doesn't help, because the problem is that the receiver doesn't have the filter. So you can't do anything at the cellular side to recover from this. Now, this is our Helsinki office. We have actually at our office there this issue present. So a base station here, antenna pointing this way, our office is over here. So this is distance about 50 meters, maybe 150 feet or something like that. Now, we are measuring with our sensor the throughput there to an AP in our office. So you can see 5 gigahertz. So there are two APs, and these are 5 gigahertz of both APs. So throughputs are about 50, 60 range here. These are 2.4. So this guy is on channel 1, very strong signal level. This is on channel 6, again, very strong signal level. Throughputs for this one are like 2 megabit per second continuously. Now again, for the same AP here, retry rates. So how are the retry rates? So this is the AP on channel 6. Retry rates in the 40s, 50s. This is on channel 1, about 12% retry rates. These are 5 gig APs. Okay, so we did some measurement. We took a lab spectrum analyzer, horn antenna pointing towards the base station here, and took some measurements. So what we saw there is that there are those two carriers that I was showing. Signal levels, peak, max hold values, minus 13 dBm, both 2100 and 1800 band, and average is about 10 dB lower. So those two carriers are sticking there. Let me see. Then I calculated what is the frequency difference between those two, and we end up into this kind of situation. So this is the other carrier, and this is where it lands. So we did some spectrum analyzer measurements. We took a laptop spectrum analyzer, and this is how it looks. So this is the spectrum. This is the center frequency of that intermodulation when you calculate those two peaks and move it here. And then we looked at what are the signal levels of the APs with the same antenna there in the same setup. The maximum AP, detected AP is at minus 79, so it's here. And we get the spectrum, high energy spectrum there visible. The signal is not there. There is nothing. There is nobody except the intermodulation product is on that frequency. And it blocks completely in practice use of that channel. So this is another view to that. We turned over the antenna the other direction, and the levels dropped radically. So this, this kind of thing may be going on if you have their high power base stations nearby. They can be cellular base stations or some other high power transmitters. It takes always two tones, so you need to have two higher power carriers. We did a project for Ofcom in UK, measuring a little bit similar case where we had one carrier at 2.3 gigahertz LTE band just next to the Wi-Fi band, and we were measuring that, does it impact to the performance of the Wi-Fi? that one carrier case did not impact the Wi-Fi performance there. But there are some very detailed reports available. These are public domain, so Ofcom has published those. So if you want to take a look, here are links as well to those materials. So that's all.